The ocean is a big place, so maybe it's not that surprising that MH370 hasn't been found. At least that's what you hear a lot of people say. It's pretty widely accepted among the general public that the seabed search failed because, well, the ocean's big. Why shouldn't it be hard to find a plane in it? But actually, the scientists who defined the search area had good reason to think that they knew where the plane had flown to, with a pretty good degree of accuracy. Last season, we talked about the 7 ping rings and how they were defined from the Inmarsat BTO data. We paid special attention to the 7th arc because investigators believed that when the plane transmitted that signal, it had run out of fuel and would impact the ocean soon. In episode 4 of this season, we talked about how the plane might have flown in the immediate aftermath of the transmission of that ping and how far it might have flown. And so how wide the search box needed to be in order for the search vessels to find the wreckage. Of course, there's another dimension to the seabed search box, the length. How far south could the plane have flown? How far north? Once we have those parameters, as well as the width from the 7th arc, we know where the plane should be. And so that's where we should search. It sounds like a daunting task, but it's helped by a really fascinating aspect of the data that we're going to talk about next. Hi, everybody. Jeff Wise back with you. Before we get into the meat of it, let me just remind you that we've got a Kickstarter going. So if you could please kick in something, that would be great. It would be really fun to see that flatbrown get in the ocean, watch those barnacles grow. I'd like to thank everyone who's pledged so far to the Kickstarter. If you haven't already, please subscribe here to the show on YouTube or sign up for the show page at findingmh370.com. You'll get a free weekly newsletter and with lots of other information about the topic of the day. Okay, let's get into it. Now, when Inmarsat scientists first looked at the ping data, it wasn't immediately obvious that that data would tell you where the plane went. After all, at the moment that it made each ping, the plane could have been anywhere along that arc. So theoretically, you could have any number of arbitrary paths that ended up anywhere on the 7th arc. And to this day, actually, you still hear people proposing routes that kind of follow a jiggly-jaggly route and hitting each ring sort of by coincidence and then winding up anywhere really on the final arc. But really quickly, when they got that data, scientists noticed that there was a super interesting aspect to this data, which I mentioned earlier. And this is that if you assume that the plane flew straight and fast, which is how planes generally are designed and used, they fly at stratospheric altitudes and they go straight because why just burn fuel wandering around? If you assume that the plane flew in this way, like most planes do, the ping rings essentially tell you where the plane flew and how fast and where its endpoint was. Okay, so to understand why, let's review how the flight went down. The plane was flying to Beijing, and then 40 minutes into the flight, it reversed course. It flew up the Malacca Strait. At 1822, it left primary radar. And at 8:25, the SATCOM gets turned back on, and we get our first ping ring. Now, because this first ping happened so soon after the last radar contact, and the plane was presumably traveling more or less the same speed, we saw it go up the Malacca Strait at about 500 knots. And planes don't really change speed that quickly. I mean, they can go slower by climbing or faster by diving, but pretty much if you're going to go from here to there, you're going to fly at a steady speed and altitude. And so if we assume that it maintained that speed, it must have taken a slight rightward turn and wound up on that first ping at a pretty narrow range of places. We could call it a point, basically, with a certain amount of inaccuracy. But so we know where this plane is pretty much at 1825. Now, the next ping arc is an hour and 16 minutes later. At 1941, we get the second ping arc. So in that time, the plane has been flying for an hour and 16 minutes, say it's 500 miles an hour. It could have gone anywhere theoretically within this green circle. And we also know that it's somewhere along the second arc. And so it has to be somewhere along this section of the second ping ring. And so from here, it then flew south and wound up on the seventh arc, assuming that, as we talked about earlier, the BFO data is correct. It tells us that the plane went south. For the purposes of this episode, we're going to assume that that BFO data is valid and that the plane did go into the southern Indian Ocean. Now, an interesting thing about the geometry of these rings is that if you assume the plane is flying straight and more or less at a constant speed, it has to fly tangentially to that orange arc, or else the speed is going to be too slow. It's an hour. It takes an hour to go from one ping ring to the next. And so if you have to travel about 500 miles in that time, whether you go faster or slower than that, which means a longer distance or a shorter distance than that, you're constrained to a pretty tight range of paths. And if you extend that path straight onwards, you wind up getting a pretty consistent range of speeds. And if you look at the speeds that are implied by the subsequent distances between each ring, you get a very consistent picture. So long as you start at a reasonable speed between 1941 and the next ping at 2041, you always wind up traveling at more or less the same speeds during the next two intervals, about 510 knots during the first interval and about 505 knots during the second. In essence, the plane's ping rings don't just narrow down where the plane was at that moment. They actually tell us how fast the plane was going. Everyone who starts playing around with the data quickly comes to the same conclusion. Like, you can't play with this data and not notice this. And some people get very excited when they look at this, they draw their lines, they do the math, and they're like, oh my God, I've solved it. I figured out how this plane flew. It really, the ping arcs seem to tell you that the plane flew straight and fast into a very narrow area of the southern Indian Ocean. So when the plane had only been missing for a very short amount of time, and it had been missing such a short amount of time that they were still searching the surface using planes and ships, this is the area that they looked at. This is where the BTO data tells you that the plane went. And so this is where the planes and the aircraft and the ships, this is where the ships and the aircraft were directed to search. They didn't see anything. And very soon after that, another idea came into the search authorities' heads, which is they figured out the BFO data. They convinced themselves that they knew what this BFO data meant, and they realized that it too had clues about how the airplane was moving, and that it too suggested a place along the seventh arc that they should look. And here we get to another of these paradoxes about MH370, because when they defined the probability area that the BFO data implied, it was further to the north, much further to the north. And so they shifted all of these search assets hundreds of miles to the north. They actually left a big gap. They moved it so far north that they wound up, there was a whole area that they never wound up doing a seabed search on. And this is where they were looking when the month time interval had passed. They knew that the battery on the black box acoustic pingers was about to run out. And so that's when they put their microphones in the ocean. They started listening, and they got this false ping, and that whole fiasco happened. So for a while, they're searching way up north, where the BFO data seems to be optimized. And this is the peculiar thing, because the BFO data tells you to look one place, the BTO data tells you to look another. Now, you would think if the same event produced all of this data together, the BFO data and the BTO data having produced by a real aircraft in a real event, should agree. And yet they don't. Why is that? Interesting question. So having these two contradictory data sets, they had to decide, okay, what do we do? Which should we believe? Where should we decide to look? They basically decided that they were right the first time. They thought, you know what, the BFO data it's complicated. It has a lot of error in it. We're just not that confident. The BTO data is quite precise. We have a lot of confidence in it, and it has a very small margin of error. So let's look at that. What does that tell us? Now, as I said, when a layman looks at this BTO data and starts drawing lines and seeing how it implies speed, you can easily come up with an endpoint that is plausible. And so if you remember, there was a whole bunch of amateur people, including myself and other people who've come out of the woodwork via the internet. And we were all working together, trading ideas. We were all drawing routes. We were doing the math. We were saying, oh, hey, look, I found this route. It ends up at such a place. The speeds are such and such. There's such and such margin of error with the BTO and BFO data. And we all got very excited. And we wound up with kind of a constellation of points that were like suggestions of where this plane could be. That was not good enough for the real scientists who were employed by the Australian government and had been put in charge of defining a search area for this plane. They wanted to develop a statistically rigorous mathematical approach that would give them not just a whole bunch of ideas of where to look, but a mathematically defined statistical distribution of where this plane might be, so that they could start at the highest probability locations and then gradually work their way outwards until they had searched all the reasonable locations. Presumably the plane must be there. They were quite confident, as I've said many times. One of the search officials said, well, we have a bottle of champagne on ice waiting for us to celebrate our happy moment where we find this plane. They were really expecting a triumph of mathematics, that they would find this plane based on on the mathematical analysis of these signals alone. So what was their approach? We've talked before about the kind of complicated analysis of the BFO data. Today, I want to talk about a similarly, not quite as daunting mathematically, but a quite interesting and a little bit non-intuitive approach that they took to define rigorously a search area where they thought the plane would be. So this is what they did. They used a mathematical technique called Monte Carlo simulations and Bayesian inference. The first one means using a computer to generate thousands of possible routes, basically making different assumptions. You could vary the altitude, you could vary the autopilot settings, the angles that it turns, whatever. You could make it make one turn, you could let it take 2 turns, or however many turns you want it to take. And then that gives you a huge universe of possible routes that you then filter out the bad ones. Take all of these routes, kind of just let anything go, and then let the computer sort through and say, okay, what are the ones that actually match the BTO data, and throw out all the others. And that will leave us with a universe of possible routes that this plane could have flown. They then, of this remaining population, they then weighted what remained based on how probable they are. And this is the Bayesian inference part. And this is what it works. This is basically how it works. If you're allowed to make a turn, that opens up a lot more possible routes that allow you to hit each ping ring and wind up on the 7th arc. But since the pilot didn't know about the BTO data and couldn't have planned to deliberately make his route match it, it would only be by coincidence that if he made a turn and still happened to match the ping rings that, as we've seen, automatically want to match a straight line route, that's all just by happenstance. And the more turns you allow the plane to make as you generate all these routes, the greater the proportion of them don't wind up matching the ping arcs. And so the less likely a route matching the ping arcs becomes. That might sound a little confusing. So here's an analogy. Let's say you read a story in the newspaper about a murder victim and he had 50 cents in his pocket. And the question I want to ask you is, what kind of coins did he have? Right? Now, there's all sorts of ways you can have 50 cents. You could have 2 quarters. You could have 5 dimes. You could have 50 pennies. You could have 2 dimes, a nickel, and 25 pennies, etc. There's a lot of different ways you could have it. But let's imagine we cut the possibilities into 2 baskets. Let's say he either had fewer than 4 coins or he had more than 4 coins. If he had fewer than 4 coins, he could only have had 2 quarters, right? And if he had more than 4 coins, he could have had 5 dimes, etc. So there's a whole bunch of different ways. And so, yes, he might have had 13 pennies, 5 nickels, etc. Really complicated. He might have just had a fistful of change. But if he had a fistful of change, there's all kinds of different values that could have come out with, right? It could have been 37 cents. It could have been 64 cents. It could have been 51 cents. And so the fact that it was exactly 50 cents makes it probabilistically more likely that he had 2 quarters than any other combination. Now, how exactly more likely he had 2 quarters versus any other combination depends on some other assumptions that you're going to have to make. There's a certain subjective element to Bayesian inference. However, it's the same general idea with these routes south. A simple route that hits all the ping arcs effortlessly is a lot more likely than a complicated route with a whole bunch of twists and turns and changes of speed and everything else that just coincidentally happens to wind up hitting all of these rings at the right time. So what I've said is just very intuitive. They had a rigorous mathematical approach to do it. They laid it out in a paper that they published so that the public could read it and understand what they were doing. The long and short of it is that they wound up with a search area that was very rigorously defined. It's very unlikely that a plane took a whole bunch of turns and wound up somewhere other than the search area. In 2016, I talked on the phone to one of the scientists who wrote this paper. His name is Neil Gordon, works at the Defense Science and Technology Group, which is a branch of the Australian government. He was the lead author of the paper, and I asked him all about it. One of the things he told me was that his model prefers simpler explanations than highly complex ones.
It prefers simpler explanations rather than highly complex ones. So if doing one turn and staying on the same autopilot mode fits the data as well as doing 35 turns, all having to be carefully orchestrated with these measurements you didn't know were going to occur, then yes, it would prefer the single turn explanation, the simple explanation, over the highly convoluted complex explanation.
Okay. Here's an example of a proposal that someone has actually made saying that this is how the plane could have flown. It's very unlikely, using Bayesian inference, that this crazy curlicue route, just by happenstance, happened to create ping arcs that all match a straight line route. And that's what gives you this endpoint distribution. Now, could the plane be outside this area? Yes, and I asked Gordon about it.
If they said to you, Dr. Gordon, where should we've got another 50,000. Should we go further north or should we go further out?
Well, if you look at the probability distribution, it would say go up north.
We can go further up north.
It spreads out a lot up north.
Oh, does it? Oh, okay.
For sure. It's quite constrained and peaked in the southern end.
Okay.
If you look at the distribution, and I guess that it's also interesting in the sense that falls right into the maximum achievable range area as well.
Sure.
But then as you move north, it's still there, but it tails off more slowly.
I see. Okay.
Which means you've got to search a larger kilometer squared area to aggregate the same probability.
So after I spoke to Gordon, the company Ocean Infinity actually stepped forward and actually did search considerably farther north, just as he had suggested would be a good thing to do. They did not find anything. And so at this point, according to their own final report, the Australian authorities don't really have any idea of where to look next. They don't think it's any further out from the seventh arc, and they don't think it's further north or south. And they're pretty sure that it's not that they overlooked it in their search. It's not on the seabed and it was like in a hole or a canyon, or maybe there was, a malfunction of the machine. They're just legitimately stumped. They are out of ideas. Of course, as viewers of this podcast will know, there is another possibility. Maybe the BFO data was tampered with and the plane didn't go into the Southern Ocean at all. And that's why they didn't find it. I actually put this to Gordon. I was already thinking that this data could have been tampered with. I thought that they might already have been on a fool's quest. I asked him, I said, before the debris was found in the western part of the Indian Ocean, and all we had indicating the plane went to the south was the BFO data, how did you guys know that the BFO data hadn't been tampered with?
I guess all I've done is process the data as given to me to produce this distribution.
Right,
yeah.
right.
At another point in our interview, he said,
"You've got to understand what our job in this investigation is. Our job is to take the data as presented to us by the expert investigators, and what do you predict as the trajectory from that?"
Effectively, in defining the search area, the DSTG set the possibility that it wasn't there to zero. That was the exercise they were engaging with. They weren't asking any questions about whether this data is good or not. There's an idea that's discussed in Tom Chivers' book about Bayesian statistics, Everything is Predictable. He talks about Cromwell's rule, which was named after Oliver Cromwell's famous proclamation, "I beseech you in the bowels of Christ, think it possible that you may be mistaken." This is reference to the fact that in Bayesian statistics, you're constantly updating your assessment of relative probabilities as new information comes in. But if you start out by giving something an initial probability of 0, no new information will ever change that, because anything multiplied by 0 is still 0. If the DSTG had granted a 0.1% probability to the possibility that their data had been corrupted, then as the seabed search whittled away the certainty as to an endpoint in the Southern Ocean, that 0.1% would have gotten bigger and bigger and bigger until ultimately it would have been quite large, certainly large enough to take notice of. This is what Todd Humphreys was talking about when I talked to him in last season. And he said,
so one of the interesting facets of Bayesian estimation is that you must update your priors when you are faced with new evidence. The failed search was new evidence. And so if I'm going into the search, before conducting the search, I'm looking through all of the data, I'm seeing its high internal consistency, I'm looking at how difficult it would be to consistently fool the sensors involved, the satellites involved, and I'm assigning a fairly low probability to any, say, strategic actors working to manipulate the data. But after a failed search, you have to, again, recalibrate. And you ask yourself, okay, given that the search failed, do I revisit this assumption that there was no chance the data were manipulated? And I think it is entirely scientific to revisit that assumption and to say, let's open up some areas of inquiry. The trouble with with applying Bayesian thinking in a really dogmatic way is that sometimes you preclude the possibility of even looking for data, looking for evidence, because you have very strong priors against such evidence.
Okay, I'll leave it at that. For now, I'd really like to thank everyone who has bought a paid subscription to this page and the show page at findingmh370.com. Thanks as always to Keely for her hard work and ideas, and to everyone else who has contributed their time and energy to the podcast. Please do throw a buck at Kickstarter if you can. It would be just so fun to get that flapper on in the water and watch those barnacles grow and finally get some closure on where that aircraft debris came from. For now, this is Jeff Wise saying, don't stop looking and don't stop asking hard questions. I'll see you next time.